Good evening everyone, good evening. I welcome you all again to the NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Hello Akhila, hello Mahvesh, hi Chitra, hello Ashwarya. Good evening everyone, welcome back people, welcome back, right? Welcome back, just give me a second, we'll be starting, yeah? Just give me a second. Okay, so people, you can let me know in the chat box if I'm audible and visible to everyone. I know we are meeting after so long, right? Right, we are meeting, I guess, after 2 weeks, yeah? Right, but from the next week, the sessions will be regular for NEET 2023 students, right? Yes? Gunasekharan, which topics did I leave in which chapter? You can let me know. First of all, just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys, right? Let me know people, let me know fast, let me know fast. Let me know fast. Hello Ishpreet, welcome. I know you're from my long-term batch, welcome. Welcome. Yes, UV, I really want to come regular for NEET 2023 students, but at the same time, the current priority is NEET 2021 students, right? So basically we have planned a lot of series for them, and at the same time I have planned series for you guys as well, right? So from now onwards, every week you'll be having two sessions, right? Every week I'll be taking 2 sessions for NEET 2023 students, but those 2 sessions are going to be marathon sessions. Like every session for the NEET 2023, I'll be taking for minimum of 2.5 hours, right? Yes, I think that will suffice, yeah? Right, perfect. Yes, Shankar, mock test will be doing on Monday. On Monday on Monday we are not doing the mock test. On Monday we are doing the super 100 questions from the chapter P block. Yeah, perfect. Okay, so before starting the session, the ones who are new to the channel, let me introduce myself. Well, my name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, right? Okay, so I think all the elites have joined in, right? I think all the elites have joined in, is that? Yes, a lot of people are joining in fast. Jesus Club, we have started the inorganic chemistry. You can watch the Super 100 series. Well, I'm done with 2 chapters, S block and chemical bonding. We have taken some 100 questions from both the chapters. You can watch that, right? Your whole chapter will be getting revised, okay? Perfecto. So the ones who are new to the channel, who have not liked the video yet, please do like the video. Share the video with your friends and do not forget to subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this NEET Elite channel, right? Perfect. Thank you, Harshil. Thank you so much. Thank you. Right? So these are the topics which we are going to cover in the tonight's discussion. We'll be starting with the electronic configuration, and in order to write the electronic configuration, you must know what is Aufbau's principle, what is Bohr-Bary's rule, what is Pauli's exclusion principle, and what is Hund's rule, right? These are the things which basically we are going to cover right here in the tonight's session. Yeah? Perfect. So you can let me know in the chat box if you people are super duper excited about this session so that I can start the session directly without wasting a lot of time. Yeah? Let me know in the chat box if you people are super duper excited. No, Abdulaziz, this is not the last session of this chapter. One more session is needed in which I'll be covering the quantum mechanical model. I have not touched the Schrodinger's wave equation yet. In the next session of atomic structure, I'll be discussing Schrodinger's wave equation with you people, okay? Right? Perfect. Okay, and do let me know once the session ends, do let me know in the comment section which chapter do you want the next, okay? Do let me know in the comment section once the session ends, right? Which chapter do you want the next, yeah? Perfect. Okay, so people, let's get started. Let's get started with the tonight's discussion. And basically what we are going to do over here, we are going to see how electronic configuration of different elements is to be written, okay? Yeah? But before talking about that, before talking about the electronic configuration, let me quickly revise certain things which I have told in the earlier sessions of atomic structure. Okay, let me just quickly revise some basic things so that there won't be any issue in writing the electronic configuration of different elements. Okay, let's assume I'm taking the element, I'm taking some atom for example. Okay, this is the nucleus of the atom. this is shell number 1, this is shell number 2, shell number 3, shell number 4, and so on, right? Okay. For shell number 1, as you all must be knowing, principal quantum number n is equal to 1, and this shell is what we call as K shell. Okay. And in this K shell, in this first shell, we have got only one subshell, if you remember. We have got only one subshell, and that subshell is what we call as S subshell. That subshell is what we call as S subshell. Okay. And S subshell only contains one orbital, and that orbital is represented by one S, for example. Okay. Right? It just contains one orbital. Let me write it over here for you. It just contains one orbital, and right, that's something which I call as S orbital, which I'm designating as 1s over here. Yes? This is something which you all must be knowing, correct? Similarly, if I talk about shell number 2, n value is equal to 2. That means I'm talking about L shell. This is the second shell which I'm talking about. In the second shell, we have got basically two subshells. In the second shell, we have got basically two subshells. Which all subshells do we have in the second shell? You all must be doing. It is going to be S subshell and P subshell, right? S and P subshell, right? And as you all must be knowing, S subshell, it contains only one orbital, whereas P subshell contains three orbitals, okay? P subshell contains three orbitals, right? Okay, so basically, if I'll ask you, in the second shell, how many total orbitals do we have? We have got total 1 plus 3, 4 orbitals in the second shell, right? Okay. Similarly, guys, if I talk about n is equal to 3, if I talk about the third shell is designated as M over here, as you all must be knowing, yeah? And in the third shell, we have got three subshells. We have got three subshells, correct? And these three subshells are basically your S subshell, P subshell, and D subshell. And we know S subshell contains only one orbital, P subshell contains three orbitals, right? And D subshell, as you all must be knowing, it contains 5 orbitals, correct? It contains 5 orbitals, right? This is your S orbital, for example. This is your Px orbital, for example. This is Py orbital. This is Pz orbital, right? This is, for example, Dxy. This is, for example, Dyz, right? This is, for example, Dzx. This is, for example, dx square minus y square. And this is, for example, dz square, right? These are the different orbitals which are present in the third shell, basically, okay? Similarly, if you talk about shell number 4, in shell number 4, you have got 4 different subshells, S, P, D, and F, whereas S subshell, it contains one orbital, P subshell again contains 3 orbitals, right? D subshell again contains 5 orbitals, and F subshell contains 7 orbitals, as you all must be knowing. We have discussed this in detail, if you remember, yeah? Okay, now people understand. Let me write one notation over here. Let's try to decode certain things from a general notation which I'm going to write. Let's say I'm writing something as 3dz square and 1 over here. Okay, I'm writing something like this. 3dz square 1. What all things can we depict by this notation over here? What all things can we depict from this notation over here? First of all, it simply means we are talking about the third shell. This 3 represents the shell number. Okay, 3 represents the shell number. And from this D, you are getting the idea of that the subshell which is containing the electron, that is your D subshell. Basically, the electron is present in the D subshell, right? In the D subshell, in which orbital electron is present? The electron is present in dz square orbital, right? And how many electrons are present in the dz square orbital? 1 electron is present in the dz square orbital. Yes, so all these things you can depict from this general notation over here. Yes, so this simply means principal quantum number is 3, right? The subshell which we have right here, the subshell in which electron is present, that is the D subshell, right? D subshell definitely has got some 5d orbitals. In that D subshell, in which orbital electron is present? Electron is present in dz square orbital, right? And at the same time, how many electrons are there? There is 1 electron, correct? Similarly, if I write something as 4p3, 4px3, something like this, we can decode this as well. It's as simple as that. It simply means the electrons are present. I mean, this simply means we are talking about the fourth shell, right? This represents the shell number. Okay? In the fourth shell, which subshell are we talking about? We are talking about the P subshell right now. Yes. In the P subshell, which orbital are we talking about? We are talking about px orbital, right? We are talking about px orbital. Sorry, I wrote 3. 3 is not possible. This is 1, for example. Okay. And this px orbital, it contains one electron. It contains one electron over here. Yes, I'm sure you all must be familiar with all these things, right? You must be familiar now with all these things because we have discussed this in detail, right? Now people, I'm moving on to the actual stuff which we have to discuss basically in the tonight's session. That's what we call as electronic configuration, right? So first thing, in order to write the electronic configuration of different elements, we need to know three rules. Three rules you must know before writing the electronic configuration of the elements, right? What are those rules basically? The first rule which I'm starting with, that's what we call as Aufbau's principle, right? That's something which we call as Aufbau's principle. What is Aufbau's principle all about? Okay. Okay, first of all, I'll ask you a general question, okay? I'll ask you a general question. Can you let me know in the chat box what was the name of the scientist who gave the Coulomb's law? Right? Coulomb's law was given by which scientist? I just want to see what you are going to say. Coulomb's law was given by which scientist? Of course, Coulomb's law will be given by Coulomb only, right? Yeah? People are using their brains, Planck's, Faraday, my God. Coulomb's law will be absolutely given by Coulomb only, right? Okay, can you let me know? Aufbau's principle will be given by which scientist? What is the name of the scientist who gave this principle? I'm talking about Aufbau's principle, right? So people are saying Aufbau was the name of the scientist who gave this principle. Let me tell you, this Aufbau, this is not the name of the scientist, it's a German word. It is a German word, which simply means to build up. To build up, okay? So remember this, right? Okay, what is this Aufbau's principle all about? As per this Aufbau's principle is concerned, let me write its statement. Let me write its statement. The electrons are to be filled. The electrons are to be filled in the orbitals. In the increasing order of their energies. In the increasing order of their energies. In the increasing order of their energies, right? What it means exactly? What it means exactly? See, first of all, as per this Aufbau's principle is concerned, the electrons are to be filled in the orbitals on the basis of their increasing energies, right? So that orbital will be getting the electrons first, which contains least amount of energy among all the orbitals, okay? So I'm simply saying that orbital, we are going to fill the electrons in that orbital first, which contains minimum energy, right? So we are going to fill the electrons in the orbitals on the basis of their increasing energies, right? Now the point is, how will we get to know which orbital has got minimum energy and which orbital has got maximum energy, right? That's something which we are going to do, right? How to get to know that which orbital has got minimum energy, which orbital has got maximum energy? There's a rule for that. There's a rule for that. What is that rule called? That rule is what we call as Bohr-Bury's rule. That rule is what we call as Bohr-Bury's rule, right? Or in the books, it will be mentioned as N plus L rule as well. N plus L. This is the rule by means of which you'll get to know which orbital has got the minimum energy, which orbital has got the maximum energy. By the way, why am I giving you this rule? Because as per Aufbau's principle is concerned, we are going to fill the electrons in the orbital on the basis of their increasing energies. Now the point is, how will we get to know which orbital has got less energy, which orbital has got more energy? That's something which will be given by something called as a Bohr-Bury's rule over here. Yes, or we call it as N plus L rule as well. Yes. Now people, as you all must be knowing, in the first shell, you have got only one subshell. In the first shell, you have got only one subshell, that is 1s, right? In the second shell, you have got two subshells. One is 2s and one more is 2p. In the third shell, you have got three subshells. One is 3s, one is 3p, one is 3d, right? And in the fourth shell, you have got four subshells, right? 4s, 4p, 4d, and so on, and so on. Okay, let's not talk about it afterwards, okay? Understand properly what I'm going to say now. See guys, first of all, this S subshell always contain one orbital, okay? So this S subshell, it will contain one orbital. This will also contain one orbital. This is p. P contains 3 orbitals, as you all must be knowing, right? This is 3s subshell, it contains 1 orbital. This is 3p, it contains 3 orbitals. This is 3d, it will be containing some 5 orbitals, as you all must be knowing. 4s will be containing 1 orbital. 4p will be containing 3 orbitals, right? That's something which you all must be knowing, correct? Now people, let me arrange them on the basis of their increasing energies. How will I be arranging them on the basis of their increasing energy? It's simple. It's simple. Use the n plus L rule. As you all must be knowing, first of all, for S subshell, the value of L is taken to be 0, right? For P subshell, the value of L is taken to be 1. For D subshell, the value of L is taken to be 2. And for F subshell, right? For F subshell, the value of L is to be taken as 3, right? This is something which you all must be knowing, correct? Now, if I talk about this 1s, what is the value of N over here? Value of N is 1. What is the value of L for S subshell? The value of L for S subshell is 0, right? So 1 plus 0 comes out to be 1. So N plus L value for 1s came out to be 1. Similarly, what is the N plus L value for 2s? N value is 2. For S, L value is 0. So 2 plus 0 comes out to be 2 again. N plus L value for this is 2, right? For 2p, N value is 2. L value for P is 1. So 2 plus 1 is 3. So N plus L for 2p is 3. Similarly, for 3s, it's going to be 3. For 3p, it's going to be 4, right? For 3d, N value is 3. For D, L is 2. So 3 plus 2 is 5, right? For 4s, N plus L value is going to be 4. For 4p, it's going to be 5. For 4d, it's going to be 4 plus 2, 6, right? These are basically the N plus L values which I wrote over here. These are the N plus L values of different orbitals which I wrote over here. These are N plus L values, correct? Now, as I told you, remember that orbital which has got the minimum N plus L value will be having the minimum energy. Have a look. Which one has got the minimum N plus L value? This orbital has got, this subshell has got minimum N plus L value, right? So this 1s is going to have minimum energy among all. 1s is going to have minimum energy among all, right? Okay. Now after this, 2s will come. After this, 2s will come. After 2s, we have got this 2p and 3s over here, which have got same N plus L value, right? Now remember, when the N plus L value will be the same, at that time you are going to decide the energies on the basis of N value. Now check in these two. Which one has got the less N value? Less N value is for 2p. So 2p comes first, then comes your 3s, right? Okay. And after this, what am I going to write? Now this 3p and 4s, both have got same N plus L value. Now decide on the basis of N. N value is less over here. So 3p will be having less energy. Then 4s will come, right? Then similarly 3d will come, and then 4p will come, and so on, right? So people, let me tell you, this is basically the increasing order of energies. This is the basically increasing order of energies. And as per our Bohr's principle, we are going to fill the electrons in these orbitals on the basis of their increasing order of their energies. That means whenever you'll be trying to write the electronic configuration, you need to fill the electrons first in 1s, then comes your 2s, then comes your 2p, then comes your 3s, then 2p, and so on, right? And we know, all your S subshells contains just one orbital. That's what we call as S orbital, right? Okay, that's what we call as S orbital. And every orbital can accommodate a maximum of 2 electrons. That's something which you all must be knowing, right? Okay, so this orbital can accommodate maximum of 2 electrons. Similarly, P subshell has got 3 orbitals, right? Px, Py, Pz. As I told you, every orbital can accommodate maximum of 2 electrons. So 2 electrons in this, 2 in this, 2 in this. So P subshell can accommodate maximum of 6 electrons. S subshell can accommodate maximum of 2 electrons. If I talk about D subshell has got some 5d orbitals, right? Every orbital accommodates maximum of 2 electrons, and we have got some 5d orbitals, so 10 electrons in this. Similarly, in case of F subshell, it can accommodate maximum of 14 electrons. This is something which you all must be knowing, yeah? This is something which you all must be knowing, correct? Right? So you got to know the increasing order of the energies of these orbitals over here, yes? Remember one important thing. This Bohr-Bury's rule, it is only applicable to the multi-electron system. It is only applicable to multi-electron system, right? It is only applicable to multi-electron species. Those species which contains, right, which contains more than, in short, remember one thing, this Bohr-Bury's rule, it's not valid for hydrogen atom. This Bohr-Bury's rule, it's not valid for hydrogen atom. Okay, remember this Bohr-Bury's rule, it is not valid for hydrogen atom. So what is the order of energies of the orbitals of the subshells in case of hydrogen atom? What is the order of energies? What is the order of energies of the subshells, of the orbitals in case of hydrogen atom? See guys, if I talk about hydrogen atom, for hydrogen atom, the energies of the subshells, it only depends on the principal quantum number n. It only depends on the principal quantum number n. Arun, you can just drag the video back. It will be a replay for you. Please stop spamming the chat box, right? Stop spamming it. You can just drag the video back. It will be a replay for you, right? Use your common sense a bit. Okay. See, what I'm talking about right here, this Bohr-Bury's rule, it's not valid for the hydrogen atom, right? It's not valid for the hydrogen atom. Well, if I talk about the subshells of the hydrogen atom, if I talk about the orbitals of the hydrogen atom, right? Their energies only depends on the principal quantum number. Right? Their energies only depends on the principal quantum number. Okay, how come? See, in case of hydrogen atom, 1s will be having least energy. Then in your second shell, you have got 2s and 2p, right? You have got 2s and 2p. Remember, 2s and 2p will be having same energies in case of hydrogen atom. Right? Okay? Yes? Now we will similarly, if I talk about the third shell contains 3s, third shell contains 3p, third shell contains 3d, right? So third shell subshells will have same energy in case of hydrogen atom, right? Similarly, if I talk about 4s, 4p, 4d and 4f, they'll be having same energy, right? And this is valid for what? This is valid for your hydrogen atom over here. Okay? Yes. So remember from now onwards, this Bohr-Bury's rule, it's not valid for hydrogen atom. For hydrogen atom, energies of the subshells, energies of the orbitals, for hydrogen atom, it only depends on the principal quantum number, right? If the subshells belong to the same principal quantum number, if the subshells belong to the same shell, right, they'll be having the equal energies. For example, if I talk about the second shell contains two subshells, right? 2s and 2p. Okay, so 2s and 2p for hydrogen will be having same energy. Similarly, 3s, 3p, 3d, they'll be having same energy. Similarly, 4s, 4p, 4d, 4f, they'll be having same energy, right? Okay. Yes. So let me know fast in the chat box if it's clear to everyone. Let me know fast. Let me know fast. Let me know fast. Let me know in the fast. Let me know fast in the chat box if everything is clear till here. Yeah. Yes, Alia. 2 sessions will be required after this. Let me know fast in the chat box if every single thing is clear. People, do it fast. Yeah? Guys, there is something called as common sense, right? If you want to see, if there is some confusion or something, you're supposed to drag the video a little back, right? It'll be a replay for you. What is the point of repeating the same thing again and again, right? Yeah? You're not class 9th students. You're not class 5th students. I hope you get it, right? You're right now in class 11th. And that too, you're doing the quantum mechanical model right now. Perfect. I'm sure it's clear to everyone, right? So this was about the Aufbau's principle, okay? Let's move on to a few more important things. See, as per your Aufbau's principle is concerned, I told you, just give me a second. As per your Aufbau's principle is concerned, according to this principle, filling of electrons in different orbitals is done in increasing order of their energies. That is, lowest energy orbital will be filled first, right? Yes, lowest energy orbital will be filled first. Okay, this is something which we have done. Bohr-Bury's rule is done, right? The orbital having less n plus L value will have less energy. In the orbitals, the orbitals which have got same n plus L value, right? Those orbitals which have got same n plus L value, right? In those orbitals, that orbital which contains the lesser value of n will be possessing the lesser energy, right? This is something which we have discussed as well, right? And this is the energy order in case of multi-electron species. 1s, 2s, then 2p, then 3s, and so on, right? But in case of hydrogen atom, as I told you, for single electron species, n plus L rule is not valid, right? Energy of the orbital for the single electron species only depends on the value of n. This is something which we have discussed again, right? This is something which we have discussed again, yeah? And for the hydrogen atom, this is the increasing order of the energies of the orbitals, right? This is the increasing order of the energies of the orbitals. Yeah? I'm sure it's clear to everyone. Perfect. Right? Karthi, hydrogen has got the other shells as well, but they are empty, okay? They are empty. Because it just has one electron. We always say in the hydrogen, for example, the electron excites. If there were no other shells, where would that electron go? Yeah? Guru Prasad, I've already started the top 100 questions for the inorganic chapters. I'm done with S block. I'm done with chemical bonding. On Monday, we'll be doing the P block elements, right? Okay, perfect. All right, now people, there is something called as degenerate orbitals. Have you heard about something called as degenerate orbitals? Have you heard about something called as degenerate orbitals? Can you let me know in the chat box? Have you heard something about the degenerate orbitals? Degenerate orbitals are the ones which have got same energy, Those orbitals in general I'm saying, okay? I'm going to give you its appropriate definition in some time, okay? You remember, first of all, degenerate orbitals are the ones which have got the same energy. For example, if I talk about hydrogen atom, right? If I talk about hydrogen atom, in the hydrogen atom, 2s and 2p has got same energy. In the hydrogen atom, 3s, 3p and 3d, they have got same energy. In the hydrogen atom, 4s, 4p and 4d and 4f, right? They have got same energy. I'm talking about hydrogen atom right now, okay? So those orbitals, basically, those orbitals which have got same energy. So these two I'm calling as degenerate, these three I'm calling as degenerate, these four I'm calling as degenerate, okay? So those orbitals, basically, which have got same energy are something which we call as degenerate orbitals, right? Let's talk about its actual and most appropriate definition. What is that? Have a look. See guys, if you talk about any subshell, let's say I'm talking about P subshell. I'm talking about, for example, P subshell, okay? Similarly, let's assume I'm talking about D subshell. Well, as you all must be knowing, P subshell, it has got some 3 orbitals, right? P subshell contains 3 orbitals. One is called as Px, one is called as Py, and one is called as Pz. Or let me represent it like this. These orbitals are basically represented with these boxes, right? This is, for example, Px, this is Py, this is Pz, right? The orbitals belonging to the same subshell, having equal energies in absence of external field, See, understand once again what I'm telling, okay? The orbitals which belong to the same subshell, those orbitals belonging to the same subshell, having equal energies in absence of electric field are something which I call as basically the degenerate orbitals, right? So this Px, Py and Pz, they will be having some same energy, right? Energy of Px is equal to energy of Py is equal to energy of Pz. So I'll be calling these 3 orbitals as degenerate orbitals, right? Similarly, if you talk about D subshell, in your D subshell there are some 5 orbitals. Right? And as I told you, the orbitals belonging to the same subshell, having equal energies, right, in absence of the external field are something which we call as degenerate orbitals. So basically, these 5 d orbitals, they have got equal energies. These 5 d orbitals have got equal energies, right? Okay, and if these 5 orbitals have got equal energies, so I'll be calling these 5 d orbitals as degenerate orbitals, right? So if you talk about the D subshell has got some, in the D subshell you have got some 5d orbitals. You have got some 5d orbitals, and all these 5d orbitals in absence of the external field will be having equal energies, and all these 5 orbitals of D are what we call as degenerate orbitals, right? I'm sure it's clear to everyone. Komula, you need to click on the link which is there in the description box of the video, then you can get enrolled in the actual Vedantu classroom, right? I'm sure it's clear till here, yes? Similarly, if you talk about F subshell has got some 7 orbitals, and all those 7 orbitals will be having same energies. I'll be calling those 7 F orbitals belonging to the same subshell, right? Having same energies. Those are what I call as degenerate orbitals. I'm sure it's again clear to everyone, right? You can let me know in the chat box fast if every single thing is clear to everyone, right? And people, at the same time, in presence of some external field, the degeneracy of these orbitals is lost basically. So right now, in absence of the electric field, all these 3 p orbitals, they had same energies, right? Now in presence of, for example, electric field, in presence of, for example, magnetic field, right? The degeneracy will be lost. For example, this will be then px, let's say this will be py, let's say this will be pz, right? Okay, so the degeneracy is lost. That means in presence of the electric or magnetic field, the energy of px won't be equal to energy of py, won't be equal to energy of pz, right? Similarly, in presence of your magnetic field or electric field, the degeneracy of these orbitals is again lost, right? So right now, in absence of electric field, in absence of external field, all these 5d orbitals, they had same energy, right? But now, in presence of the external electric or magnetic field, what is going to happen? Splitting of these orbitals will take place, right? Okay, so remember, in presence of the external electric or magnetic field, the degeneracy is basically lost. Okay, so in presence of the external field, for example, they are going to lose their energies, for example, like this. Okay, I'm just making you understand what exactly happens. That's something which I'll be teaching you in your class 12th coordination chemistry. Okay, so just remember in short, those orbitals which belong to the same subshell having same energy are called as degenerate orbitals, right? Those degenerate orbitals, they have got same energy in absence of the external field, but in presence of the external field, what happens? The degeneracy is lost, right? This is something which you must remember. That's it. Okay, perfect. Right? Is everything clear till here? Is everything clear till here? UV, bro, you need to check class 9th chemistry, bro. I think you're in wrong section. Yeah? Perfect. Moving on to one more. Moving on to a few more things. See, as I told you, your p subshell, it has got 3 degenerate p orbitals. Similarly, if I talk about d, you have got 5 degenerate orbitals. And I've told you, orbitals of a particular subshell are degenerate in absence of the external field. In presence of the external magnetic field or electric field, they split into different energies, hence degeneracy is lost. Yeah? I'm sure it's clear to everyone. Okay? Perfect. Right? Let's move on. There is one more rule which you need to take into account, which you need to learn before writing the electronic configuration. What is this? What is this rule all about? Okay, this is something which we call as Pauli's exclusion principle. Okay, what is this Pauli's exclusion principle all about? What is this Pauli's exclusion principle all about? See, I'm going to write its 2 statements. These are the 2 statements for the Pauli's exclusion principle. As per the first statement of Pauli's exclusion principle is concerned, no 2 electrons in an atom can have same set of 4 quantum numbers. What does that mean? For example, if I take any atom, for example, if I talk about oxygen, right? Its electronic configuration is 1s2, 2s2, 2p4. I'm just showing you. I'll show you exactly how it's to be written, okay? This is the electronic configuration of oxygen, okay? This is basically like this. This 1 is containing 2 electrons, 2 is containing 2 electrons, and 2p containing 4 electrons. It's something like this. It's something like this. I'll show it to you in some time, okay? So people, if I select any of the 2 electrons right now, for example, I'm selecting this electron, just a second. For example, I'm selecting this electron, and at the same time, I'm selecting this electron. I'm selecting some 2 random electrons. See, corresponding to this electron, there will be some 4 different quantum numbers associated with this electron. Okay, the first quantum number, that's the principal quantum number for this electron. Principal quantum number for this electron is 1, right? Now it's an S subshell. It's an S subshell. For S subshell, the value of L is 0, right? Okay. If the value of L is 0, that means the value of M is also 0 for this electron. Now spin, is it clockwise or anti-clockwise? It's anti-clockwise spin. So spin value is -1/2, for example. So these are the 4 set of quantum numbers for this electron which I've chosen. Yes, right? Yes. Now people understand. If I talk about this electron, okay, what are the 4 different quantum numbers which are associated with this electron? First of all, this electron is in second shell, so n value is 2, right? If n value is 2, see, it's in p subshell. For p subshell, the value of L is 1, right? If the value of L is 1, so I'm selecting the value of M as -1, for example. Okay, for example, right? L value, see, it's clockwise spin, so S value, not L, S value over here, spin will be +1/2, correct? +1/2, right? So I selected some 2 random electrons and I wrote their quantum numbers, right? I wrote their quantum numbers. As per your Pauli's exclusion principle is concerned, no 2 electrons in an atom can have same set of 4 quantum numbers, right? Yes, you can check it out. See, n value 1, n value is 2, different, right? Different. So quantum numbers are different, okay? Now people, understand one more thing. See, if I'm selecting 2 electrons in a particular atom, right? Okay, one electron, it has some 4 quantum numbers associated with it. One more electron, it has some 4 quantum numbers associated with it. Out of the 4 quantum numbers of each, 3 quantum numbers can be same, but 1 quantum number will be different. Okay, right? No 2 electrons in an atom can have same set of 4 quantum numbers. Okay, there will be some kind of difference in between. I'm sure it's clear to everyone, right? Yes, perfect. And at the same time, remember, an orbital can accommodate maximum of 2 electrons, that too with opposite spin. For example, if I talk about S subshell, S subshell contains only one orbital, that's S orbital. And how do I represent this S orbital? It's represented like this, right? An orbital contains maximum of 2 electrons, and those 2 electrons with opposite spin. One is clockwise, one is anti-clockwise, right? At the same time, if I talk about P subshell contains 3 p orbitals. One is called as px, py, pz, right? If I talk about P subshell, as you all must be knowing now, it contains 3 p orbitals. One is px, py, pz, right? See, there are 3 orbitals. Every orbital contains 2 electrons, and those 2 electrons are paired in opposite spin, right? Remember this thing as well. Okay, an orbital, it accommodates maximum of 2 electrons, and those 2 electrons which the orbital is accommodating, those 2 electrons are present with opposite spin. If one electron is going with clockwise spin, one more electron will be going with anti-clockwise spin. I'm sure it's again clear to you. Yeah, perfect. See, this is something which I have already told you. Number of orbitals in a shell. If you want to calculate the number of orbitals in a shell, it is given by the formula n square, right? For example, if I talk about the first shell, for first shell n value is 1, so 1 ka square is 1. So there is only one orbital present in shell number 1, right? Similarly, if I talk about shell number 2, n value is 2, so 2 ka square is 4. There are total 4 orbitals present in shell number 2. Similarly, shell number 3, 3 ka square, 9. So there are total 9 orbitals present in shell number 3, and so on, correct? Whenever you need to calculate the total number, the maximum number of electrons present in a particular shell, the maximum number of electrons present in a shell is given by 2n square, where n is the principal quantum number, right? As simple as that. Yeah? Perfect. Let's move on. And can you let me know the answer of this question? This is a very simple question. I want you guys to answer this question over here, right? Let me know its answer first. I just want to see whether you got the concept or not. Let me know first in the chat box. I really want to see whether you got the concept or not. See, that's where you guys are making the mistake, right? This question I gave deliberately to you guys. I gave this question deliberately to you guys. And majority of, all of you are saying, except Darshini, all of you are saying 10 electrons, right? 10 is not the answer, 2 is the answer. What is the reason for it? Have a look. It's very simple. The question says, how many maximum electrons can be accommodated in 3D, over here is mentioned 3D orbital. He's not saying 3D subshell. If the question was something like this, 3D subshell, then at that time, we know 3D subshell. D subshell contains some 5 d orbitals, and every orbital contains maximum of 2 electrons. So there would have been total 10 electrons in 3D subshell, right? But this is 3D orbital. He's talking about the one of the orbital of 3D. He's talking about one of the orbital of 3D, right? For example, he's talking about this orbital of 3D, right? It can accommodate maximum of 2 electrons only. So answer of this question is going to be 2. Yeah, that's how you need to use your brain. Correct? Correct? Right? Okay, I'll ask you one more question about it. How many electrons are present in, how many maximum electrons can be accommodated in 2p subshell? How many maximum electrons can be accommodated in 2p subshell? Can you let me know its answer fast? Can you let me know its answer? How many maximum electrons can be accommodated in 2p subshell? I'm asking. 2p subshell. The answer will be 6, because I'm talking about 2p subshell. P subshell contains 3 orbitals, and every orbital accommodates maximum of 2 electrons. So total 6 electrons, yeah? Okay, if the question is like this, how many electrons are accommodated in 2p orbital? How many maximum electrons are accommodated in 2p orbital? What is the answer now? Now the answer is 2. Now the answer is 2, because I'm talking about 2p orbital, yeah? People, top-notch 100 series, its next session will be on Monday, and the session is on P block at morning 9 a.m., right? Okay, I'm sure. Exactly, people, wonderful. Yes, you all are perfectly right, yeah? Okay. All right, there is one more rule which you need to know before writing the electronic configuration. That's something which I call as Hund's rule, right? People, have you discussed this Hund's rule before? It's again a very simple rule. I'm sure you all must be knowing about it. What is this Hund's rule all about? What is this Hund's rule all about? What is this Hund's rule all about? Yes, UV, you are perfectly right. Exactly. Mariam is saying it is bus seat rule. Exactly, nice, nice. I liked it. Nice analogy this is. It's a bus seat rule. See guys, let me make it simple for you. If I talk about, let's say p subshell. If I talk about p subshell, right? P subshell has got how many p orbitals? How many orbitals it has got? It has got 3 orbitals. One is called as px, one is called as py, one is called as pz, right? Similarly, if I talk about d subshell, right? D subshell has got some 5 orbitals, 1, 2, 3, 4, 5, correct? Okay. In absence of electric field and magnetic field, these are degenerate. In absence of electric and magnetic field, these are degenerate. They have got same energies, right? Okay. Now, when we start filling these orbitals, when we start filling the degenerate orbitals, pairing won't be done. Pairing won't be done unless each degenerate orbital gets one electron each, that too with same spin, right? See, one upward spin, one upward spin, one upward spin. Once every degenerate orbital gets one electron, then pairing is going to start. Then pair is going to start like this, right? Okay. This is the simplest statement of it. This is the simplest statement of it. See, if we talk about the d subshell, it has got some 5 d orbitals, right? These are five degenerate d orbitals. They have got same energy. Now, people, pairing won't be done. Pairing won't be done unless each orbital gets one electron each. That too, each of the electrons should have same spin. Once each degenerate orbital gets 1 electron each, yes, then only pairing will start. Then only pairing will start like this, right? Okay. Why it happens basically? Why it happens basically? Can you let me know its answer? Why it happens? Can you let me know why it happens? Abdulaziz, I'll be doing 3 groups. 3 groups I'll be doing on Monday, right? Okay. Now people, let's exactly see why it happens. Let's exactly see why it happens. For that, you need to understand this statement over here. See guys, according to this principle, according to Hund's rule of maximum multiplicity, out of different arrangements of same electronic configuration, the arrangement which has the highest multiplicity will be more stable. The arrangement which has got the highest multiplicity will be more stable. What does that mean? What does that mean? First thing you must know what is multiplicity and how it is calculated. Understand properly what I'm saying. Remember first thing, multiplicity is calculated by the formula 2 multiplied by s plus 1. 2 multiplied by s plus 1. This is how we calculate multiplicity. 2s plus 1. What is this s over here? S is the sum of the spin. Sum of the spin. What is that sum of the spin? You'll get the idea in some time. Just wait for it. Understand. If I talk about P3 configuration, well, I can mention P3 configuration like this as well. I can mention P3 configuration like this as well, right? Okay. See, right now I have no idea about the Hund's rule, correct? So I'm making P3 configuration like this as well as this. These are 2 different configuration of your P3 over here, right? Okay. Now we will understand. What I'll be doing, for this configuration I'll be calculating the multiplicity. For this configuration as well I'll be calculating the multiplicity. Okay. For both the configurations I'll be calculating the multiplicity. And how do we calculate this multiplicity? 2 multiplied by s plus 1. What is s? S is the sum of spin of all electrons. See, this one is showing, for example, plus 1 by 2 spin. This one will be showing minus 1 by 2 spin. This is again upwards, so this one will be showing plus 1 by 2 spin, right? Plus 1 by 2 spin, correct? Just do the sum of all these spins. Do the sum of all these spins. Plus 1 by 2, minus 1 by 2, cancelled out. So total spin of this configuration is plus 1 by 2. Yes. So S value over here is plus 1 by 2. S value over here is plus 1 by 2. The sum of these 3 over here comes out to be plus 1 by 2. Yeah. Okay. So if the sum of these 3 came out to be plus 1 by 2, put the value of S as plus 1 by 2 into this equation, you get the value of M as 2. Put the value of S as 1 by 2. So 2 got cancelled, 1 plus 1 came out to be 2. Right. So multiplicity in case of this type of configuration is 2 over here. Yes. Now look at this one. See, look at this configuration. This is again the same P3 configuration only. This is again the P3 configuration. right? Now people understand. If this is, for example, plus 1 by 2, this is of same spin, plus 1 by 2, this is of same spin, plus 1 by 2. If I do the sum of these spins, plus 1 by 2, plus 1 by 2, plus 1 by 2, how much that is? That is plus 3 by 2. Put the value of S into this equation, right? S value over here is plus 3 by 2. Put the value of 3 by 2 over here. So the value came out to be 4. So multiplicity over here is 4. As per Hund's rule, wherever multiplicity will be more, that configuration is going to be more stable. That configuration is going to be valid. Okay? Among these two configurations, these were same P3 configurations, right? These were same P3 configurations, right? This was one of the P3 configuration, this was one of the P3 configuration, right? I calculated the multiplicity, yes? And over here, multiplicity came out to be more. And as per Hund's rule, wherever multiplicity comes out to be more, that configuration only is going to be more stable, right? Let me give you one more example so that things will get clear to you, right? Let me give you one more example. If I talk about D5 configuration, let me, for example, make one D5 configuration like this. Okay, random D5 configuration, 1, 2, 3, 4, 5. This can be D5 configuration. Now that's a different debate. Is it the proper or not, right? Is it the correct one or not? That's a separate debate. Let's not go into that, right? D5 configuration over here, I'm making it in this way as well. 1, 2, 3, 4, 5. One electron here, one electron here, one here, one here, one here, right? This again D5 configuration. Now people understand. Let's calculate the total spin of electrons. See, plus 1 by 2, minus 1 by 2, cancel out. Plus 1 by 2, minus 1 by 2, cancel out. Plus 1 by 2. So total spin over here is plus 1 by 2. What is the total spin over here? Plus 1 by 2, 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 right? How much it's going to be? It's going to be plus 5 by 2. Total spin over here is plus 5 by 2, right? This is the total spin, correct? Total spin over here is plus 5 by 2, for example. Well, you got the spin, you got the total spin, right? Put the spin value into this equation, right? 2 multiplied by 1 by 2, 2 multiplied by 1 by 2. So the multiplicity over here will be again 2. Multiplicity over here will be again 2. What about the multiplicity in this case? Put the value of S as 5 by 2. This is 5 by 2. 2 and 2 gets cancelled. So 5 plus 1 came out to be 6. So multiplicity is 6. So where is the multiplicity more? Over here, multiplicity is more. Wherever multiplicity will be more, that configuration is going to be more stable, right? So which one among the two configurations is more stable? This is the actual D5 configuration which is more stable. What is the reason for that? Due to more multiplicity. In nutshell, can I say pairing in the degenerate orbitals, pairing of electrons in the degenerate orbitals won't be done unless each degenerate orbital gets one electron each. Yeah? Can you give me some confirmation in the chat box if it's clear to everyone, right? I hope you got the Hund's rule now. Yes? No, UV, this session is not about to end. I'll take a lot of time. Wait. Right? We have got half an hour more. Right? We are meeting after so long, correct? I won't be able to end it. Yeah? Okay. Let me know first of all in the chat box if every single thing is clear. Okay, perfect. So I'm sure your Hund's rule of maximum multiplicity is clear, right? Okay, this is P4 configuration, right? For P4 configuration, you can calculate total spin. Once you get the total spin, right? Once you get the total spin, put the total spin value into the multiplicity equation, get the multiplicity. Multiplicity of this configuration is coming out to be more, so this is the correct configuration. This is the correct configuration. P4 configuration, this is the incorrect one, this is the correct one, right? This is the correct one. I'm sure it's clear to everyone. Yeah? Okay. So this is a note which I have been telling you for so long. Pairing in the degenerate orbitals won't occur unless the orbital gets one electron each with same spin, right? Yes? Perfect. Now let's try to write the electronic configuration. I'm sure you're clear with all these three rules, right? Now let's try to write the electronic configuration and let's try to see some exceptional electronic configurations as well, right? Let's try to see the reasons of exceptional configurations, right? All those things I'll be letting you know right here. Guys, I'm not ignoring anyone, okay? It's just the chat box is continuously coming up. I cannot read all the chats. That's the reason. Okay. So first of all, in order to write the electronic configuration, which all three rules we need to take into consideration. One is going to be your Aufbau's principle, second one is going to be the Pauli's exclusion principle, and the third one is going to be the Hund's rule of maximum multiplicity, right? Now, let's use these rules and let's try to write the electronic configurations over here, okay? First of all, the increasing order of energies of these orbitals, right? 1s, 2s, as per Bohr-Bury's rule. If you do not remember the Bohr-Bury's rule, no issues at all. You can remember it like this as well. Well, this is something which you have discussed in your earlier class as well. 2s, 2p. This is, for example, 3s. This is 3p. This is 3d. This is, for example, 4s. This is 4p. This is 4d. This is 4f, right? In your earlier class 9th standard, right? They used to do it like this, okay? This is 5s. This is 5p. This is 5d. This is 5f, right? This is, for example, 6s, this again 6p, this is 6d, this is 6f, right? This is 7s and so on. Now what we are going to do, just put an arrow over here, like this. Put one more parallel arrow over here. Put one more parallel arrow over here. Put one more parallel arrow. One more parallel arrow. One more parallel arrow, right? One more parallel arrow, right? Okay. Now what you'll be doing after this, join this arrow with the tail of the second arrow. Join this arrow with the tail of the second arrow. Join this arrow with the tail of second. Join this with the tail of next one. Join this with the tail of second. Join this with the tail of second, right? Now follow the order. Now follow the order. See, I started from 1s, then I'll come to 2s, then I'll come to 2p, 3s, then I'll come to 3p, 4s, and so on, right? This is the order of increasing. This is the increasing order of energies of these orbitals over here, right? So I'll first of all write 1s. After 1s, I'll be writing 2s. Then after 2s, it's going to be 2p, then 3s, then 3p, right? See guys, 3s, then 3p, then 4s, then 3d, right? 4s, then 3d. After your 3d, then 4p, 5s, right? This is 4p, this is 5s, right? This is 5s. After 5s, you are going to write 4d, 5p, 6s. This is 4d, after 4d, 5p, then your 6s. This is the increasing order of energies. This is the increasing order of energies of these orbitals over here, okay? Now, first of all, people, you wrote the increasing order of energies of these orbitals over here, of these subshells over here, okay? Now it's time to write the electronic configuration. We know S subshell contains only one orbital. This is again S subshell, one orbital. This is P subshell, it contains 3 orbitals, right? This is S subshell, 1 orbital. This is P, it contains 3 orbitals, right? This is S, 1 orbital. This is D, it contains some 3 orbitals. This is, D contains 5 orbitals, correct? D contains 5 orbitals. Let me write it till here, okay? Let me write it till here. Rest all the other things you know. If I talk about hydrogen atom, in the hydrogen atom, atomic number is 1. That means there is only 1 electron. So that 1 electron will go here, right? So its electronic configuration becomes 1s1. Okay. Similarly, if you talk about helium, for helium, there are, for example, 2 electrons. There are 2 electrons, right? Okay. 2 electrons. 1 electron is already filled over here. So 1 more electron over here as per Aufbau's principle, right? Yes. So first of all, we have to fill these electrons in the orbitals on the basis of their increasing energies. This orbital has got minimum energy among all, so this should be completely filled. So its configuration is going to be 1s2, right? Okay. If I talk about lithium, there are 3 electrons, right? So it's going to be 1s2, 2s1, right? 1 electron over here. Similarly, hydrogen, helium, lithium, then we have beryllium, for example. Beryllium has got 4 electrons, right? So it's going to be 1s2, 2s2, right? 1s2, 2s2, 4 electrons over here like this. Yeah, as simple as that. Similarly, if you talk about few more elements, let's talk about few more elements. For example, I'm talking about boron. Boron has got total 5 electrons, right? So it's going to be 1s2, 2s2, 2p1, correct? So 4 electrons already filled. Now the 5th electron comes here, right? For carbon, 6 electrons, right? It's going to be 1s2, 2s2, 2p2, correct? Okay. Now the next electron, am I going to pair it over here? No, these are degenerate orbitals. I have to fill it right here first. Pairing won't be done unless each degenerate orbital gets 1 electron each. Yeah? Yes. Now, if you talk about nitrogen, it has got 7 electrons, right? It's going to be 1s2, 2s2, 2p3 configuration. So this is 1 more electron here. This is for nitrogen. Similarly, all the other things you know. If I talk about sodium, there are 11 electrons, right? There are 11 electrons. 1s2, it's going to be 2s2, it's going to be 2p6, it's going to be 3s1. Okay. So this is 1 more, this is 1 more, this is 1 more, and this is 1 more. This is the electronic configuration of nitrogen. Yeah. If you talk about the electronic configuration of, for example, chlorine, or alright, oxygen. How many total electrons it has? 60. How many total? Not oxygen. Sorry. If I talk about sulfur, how many total electrons it has? Atomic number is 16. That means 16 electrons, right? So it's going to be 1s2. It's going to be 2s2. It's going to be 2p6. It's going to be 3s2, right? It's going to be 3p4. So total 16 electrons. So 3p4. 3p4 will be like this: 1, 2, 3, and 4 over here, right? I'm following all the rules. I'm writing the electronic configurations. Okay. Now, people, if you look at chromium, its atomic number is 24. Its atomic number is 24, right? If you look at chromium, its atomic number is 24. What is its, it has got some 24 electrons. What is its expected electronic configuration? You can write it, I'm sure about it. You can write the expected electronic configuration for it. The way I wrote it for the other elements, in the similar way, you are going to write the electronic configuration of chromium as well, yeah? Okay, understand. It's going to be 1s2, 2s2, 2p6, right? 3s2, 3p6, right? Okay, after 3p what comes? 4s. So it should be 4s2, it should be 3d4. This is the expected electronic configuration of chromium. This is the expected electronic configuration of chromium, right? Yes, this is the expected electronic configuration of chromium. Yeah, but this is not the actual one. This is not the actual one. Why is that? See guys, this 4s, it contains 2 electrons. This 3d, it is right now containing some 4 electrons, 1, 2, 3 and 4, correct? I'm talking about these 2 orbitals. I'm talking about these 2 subshells. Let me first of all tell you, the energy difference between 4s and 3d is not that much. Or I'll say, the energy of 4s and 3d is almost same. So you can consider these two as degenerate ones. You can consider these two as degenerate ones, right? Because the energy gap between these two is negligible, right? So one of the electron from 4s enters over here, okay? If one of the electron from 4s enters into here, so its configuration becomes 4s1 3d5, 4s1 3d5. Or normally we write the less principal quantum number in the front, then comes the more principal quantum number. It is written like this, 3d5 4s1. It is written as 3d5 4s1, right? Okay, so if I talk about the actual electronic configuration, of chromium, it's not going to be 4s2 3d4. It is going to be, let me erase it, it's going to be 3d5 4s1, right? One of the electron from 4s entered into 3d. Why it happened? When the electron from 4s entered into 3d, what happened basically? This 3d became half filled. And remember, half filled configurations are considered to be very, very, very stable. Okay, so in order to get the half filled configuration, which is considered to be very, very, very stable, one of the electron from 4s entered into 3d, right? So as to gain some extra stability, right? Now the point is, why half filled configurations are more stable? There is a reason for that as well, which I'll be letting you know in some time. Okay, right? So first of all, this is the actual electronic configuration of what? This is the actual electronic configuration of your chromium. In the similar way, let me write the actual electronic configuration of copper as well. People, I hope you're noting down every single thing with me. Copper, its atomic number is 29, right? Its atomic number is 29, okay? What is its expected electronic configuration? I'm only writing the outermost electronic configuration now. Its outermost electronic configuration is expected to be 3d9 4s2. It's outermost I'm talking about. Yes? Okay? But this is the expected one. These are 5d orbitals. 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is 4s2. Right? This is the expected electronic configuration. But people, since we know the energy gap between 3d and 4s is not that much, it's negligible, they are almost degenerate. So one of the electron from 4s enters into 3d, right? So the actual electronic configuration becomes like this. The actual electronic configuration becomes 3d10 4s1. This is the actual electronic configuration. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is 4s1. Okay. Why it happened? Why the electron entered from 4s into 3d? There is a reason for that. Okay. Remember, when the electron entered from 4s into 3d, can I say I got the completely filled configuration? This is the completely filled configuration. And again, completely filled configurations are considered to be highly stable. highly stable. So in order to get the extra stability due to the completely filled configuration, one of the electron from 4s entered into 3d. That's why its actual electronic configuration is 3d10 4s1. It's not 3d9 4s2. Yeah? Right? I'm sure it's clear to everyone. I'm sure it's clear to everyone, right? Okay. UV, these are two exceptions. You need to remember them. Okay? You need to remember them. That's it. Right? Perfect? Perfect, guys? Clear to everyone? Yeah? Yes, only these two you are going to remember. Rest, there are some other exceptions as well, which I'll teach you in the D and F block elements. Okay? There is something called as gadolinium, right? Perfect? Okay. Right. Okay, got it. Now people, remember this order as well. If I talk about the stability of electronic configurations, stability of electronic configurations. Stability of electronic configurations. Remember, completely filled configuration is considered to be maximum stable, followed by half filled configuration, right? Followed by partially filled configuration. Followed by partially filled. Partially filled means, for example, P4 configuration. P4 is partially filled. It's neither complete filled nor it's half filled. It's partially filled, right? Okay. So remember this order as well. Sometimes you might need this order in the questions. Yeah, I'm sure it's clear to everyone. Now the point is the extra stability for half filled configurations and fully filled configurations. Okay, what is the reason for extra stability for half filled and fully filled configurations, right? What is the reason for that? Okay, understand. For example, I'm writing D4 configuration right here, and over here I'm writing D5 configuration. Okay, D4 configuration will be like this. Just have a look. These are 5 d orbitals, right? 1, 2, 3, and 4. This is D4 configuration. And if you look at D5 configuration, this is how your D5 configuration looks like. Okay, right? If I'll ask you, which configuration is more stable? I told you a few minutes back. Which configuration is more stable? The first one or second one? I'll say this configuration is more stable. Why? Because it's half filled. It's half filled, right? Now the point is why it's more stable. Why it's more stable? There are 2 reasons for that. Number 1, the first reason, D5 configuration is more stable than that of D4 configuration. What is the reason for that? The first reason is symmetry. It's a law of nature, people. Symmetry leads to stability. Symmetry leads to stability. Can you let me know, first of all, among the 2 configurations, which one is more symmetric? Which one is more symmetric? Which one is more symmetric? I'll say D5 configuration, it is the more symmetric distribution of electrons, right? D5, it is the more symmetric distribution of electrons, and symmetry leads to stability. So the first reason, due to the symmetric distribution of electrons, D5 configuration is more stable, right? Yes? Right? Exactly. This is one of the reasons. Second reason is something which we call as exchange energy. There is something called as pairing energy as well, but I'm not going into that detail, right? We'll be talking about something called as exchange energy over here. Okay? Now people, what is this exchange energy all about? See, if I talk about D4 configuration, right? We have got some 4 electrons with the same spin. We have got some 5 electrons with the same spin, right? Now, these are first of all the degenerate orbitals, yeah? Can I say something like this? Can I say this electron can exchange its position with this electron, right? The same electron could have exchanged its position with this one as well, right? The same electron could have exchanged its position with this one as well, right? The same electron could have exchanged its position with this electron, but over here we do not have any electron. So this electron can exchange its position with 1, 2, and 3 electrons over here. So how many exchanges are possible for this electron? For this electron, 3 exchanges are possible, right? Similarly, for this electron, how many more exchanges are possible? See, this one is already taken into consideration. Now it can go here, right? The same one can come here, right? It can go here, right? The same one can come here. So 2 exchanges are possible for this electron. Similarly, there'll be 1 exchange possible for this electron. So total, how many exchanges are possible in this configuration? 3, 2, 5, 1, 6. 6 exchanges are possible in total. 6 exchanges are possible in total. Remember, more the exchange, whenever the electron exchanges its position over here, energy is released basically. That energy which is released due to the exchange of electrons. Okay, and exchange of electrons takes place between those electrons which have got the same spin, right? If there was one electron like this with the opposite spin, then the exchange wouldn't have been there. Yeah, there wouldn't have been any sort of exchange, right? Okay, so how many exchanges are possible right here? 6 exchanges. During every exchange, energy is released, and that energy is what I call as exchange energy. Remember, more the energy released during the exchange of electrons, more is the stability, right? So over here, how many exchanges are possible? 6 exchanges are possible. Now let's count the exchanges which are possible in this one. See, 1 exchange, 2nd exchange, 3rd one, 4th one. So 4 exchanges for the first electron, 3rd exchange for the second, 2 exchange for the second, 1 exchange for this one. 4 plus 3, 7, 7 plus 2, 8. Sorry, 4 plus 3, 7, 7 plus 2, 9, 9 plus 1, 10. So total, how many exchanges are possible in this case? There are total 10 exchanges possible. More the exchange, more the energy released, right? More the energy released, more the stability. So exchange energy in case of D5 configuration is more than that of exchange energy in case of D4 configuration. That's why we say D5 configuration is more stable. I'm sure it's again clear to everyone, right? Yes? Let me know fast in the chat box if it is clear. Is it clear to everyone, right? Now, I'm sure all of you are familiar with certain important things about the electronic configuration, like how to write the electronic configuration, right? There are a few more things which I would like to share with you. Few more things about this electronic configuration, right? I'm sure every one of you would have seen the periodic table, right? If I talk about group first elements, right? If I talk about lithium, if I talk about sodium, potassium, rubidium, cesium, right? These are what I call as group first elements. Group second elements, beryllium, magnesium, calcium, strontium, barium, right? These are what I call as group second elements, okay? Similarly, on the extreme right of the periodic table, we have got some 18th group elements, which are called as noble gases, right? They start from helium, neon, argon, krypton, xenon, correct? Just before this, there are group 17 elements, as you all must be knowing, right? Group 17 elements. Group 17 elements, what they consist of? They consist of, just a second, fluorine, chlorine, bromine, iodine, astatine, okay? And over here, we have got radon as well. Yes. If I talk about group 16 elements, group 16 means oxygen family, oxygen, sulfur, Se, Te, Po, right? Similarly, if I talk about group 15 elements, that is nitrogen family, right? Nitrogen, phosphorus, arsenic, antimony, bismuth, correct? If I talk about group 14 elements, carbon, silicon, germanium, then what do we have after this? Carbon, silicon, germanium. What do we have after this? I forgot. Can you let me know? Can you remind me? Carbon, silicon. Some people are saying helium. Arre yaar. Some are saying magnesium. Some are saying gallium. Gallium is a group 13 element, bro. Okay, yeah. This is tin, this is lead. Yeah? Okay, yes, got it. Someone is saying strontium. Bro, this is strontium. Okay, if I talk about group 13 we have got boron, we have got aluminium, we have got gallium, we have got indium, we have got thallium, right? Okay. Now people, what I would like to share with you right now. What is that? See, this is group first, this is group second, right? If you look at the electronic configuration of lithium, what is the electronic configuration of lithium? Lithium has got the hydrogen, helium, lithium. It has got atomic number of 3, 1s2, 2s1, right? Its configuration is 1s2, 2s1. Its configuration is 1s2, 2s1. If you want to write the outermost electronic configuration of sodium, which is just next to lithium, you'll be simply writing it as, its outermost configuration you'll be writing as 3s1, right? Its outermost configuration you'll be writing as 4s1. This will be 5s1. This will be 6s1, outermost configuration. Similarly, if you write the outermost configuration of Be, beryllium, it's 1s2, right? Hydrogen, helium, lithium, beryllium, right? 1s2, 2s2, correct? So let me write the outermost, it's 2s2. So if you want the write the electronic configuration of magnesium, it will be simply 3s2. This will be simply 4s2. This will be 5s2. This will be 6s2. Simple like this, right? If you talk about the electronic configuration of helium, right? It's 1s2, correct? It is 1s2, right? We know it. If you want to write the electronic configuration of neon, it's 1s2, 2s2, 2p6, right? It's 2s2, 2p6. This will be 3s2, 3p6. This will be 4s2, this is 4p6. This will be 5s2, 5p6. Similarly, 6s2, 6p6, right? If you look at the electronic configuration of group 17 elements, right? What is the outermost configuration of fluorine? It's 2p5. It's 2p5, right? It's 2p5. This will be 3p5. This will be 4p5. This will be 6p5. This will be 7p5, right? This is 4p5. After 4p5, I'll be writing 5p5. This is 6p5, yeah? Right? And similarly, if I talk about oxygen, this is 2p4 configuration, outermost configuration, 2p4. This will be 3p4. This will be 4p4. This will be 5p4. This will be 6p4, right? Similarly, nitrogen, this is 2p3 configuration, outermost. This will be 3p3 configuration. This will be 4p3 outermost configuration, 5p3 outermost configuration, 6p3 outermost configuration. Similarly, you can write for the other elements as well, right? If you talk about the carbon family, this is 2p2 configuration, this is 3p2 configuration, this is 4p2 configuration, this is 5p2 configuration, this is 6p2 configuration, and so on, right? This is similarly 3p1, 4p1, 5p1, 2p1, 3p1, 4p1, 5p1, 6p1 configuration, right? Yeah? This is how you remember the outermost configuration of different elements. This is how you remember the outermost configuration of different elements, yeah? Okay. Now people, let me ask you certain questions by means of which I'll get to know whether you got the concepts clearly or not. See, chromium, fully filled, everything is discussed in detail, right? Copper, its configuration is discussed, right? Symmetrical distribution, exchange energy, right? More the exchange, more the stability. Okay, there is something called as magnetic moment. There is something called as magnetic moment. How do we calculate magnetic moment in case of different elements? In case of different elements or different ions? See guys, understand. Magnetic moment, or you call it a spin magnetic moment. You call it a spin magnetic moment. It's represented by mu. It has got the formula of under root of n into n plus 2. Bohr magnetron. There is a special type of question asked in which you are supposed to calculate the spin magnetic moment, right? Yes? Right? Now we will understand properly. This n over here, it's not the principal quantum number. It represents the number of unpaired electrons. It represents the number of unpaired electrons, right? Whenever you'll be having any species, whenever you'll be having any element, whenever you'll be having any ion with unpaired electrons, right? Or let me write it over here. If mu, magnetic moment, spin magnetic moment for any species is 0, that species is said to be diamagnetic. That species is said to be diamagnetic. If mu is non-zero, that species is said to be paramagnetic. That species is said to be paramagnetic, right? For example, I'm starting with something called as, for example, Fe di positive. Let's say I've got Fe di positive, right? I need to calculate the spin magnetic moment of this Fe di positive, right? I need to see whether this is paramagnetic or diamagnetic. How do I check it? See. First thing, I'll be writing its outermost configuration. Its outermost configuration is 3d6 4s2. Its outermost configuration is 3d6 4s2. But this is Fe di positive. That means you have taken 2 electrons out. So let's take those 2 electrons out. Those 2 electrons have to be taken out from the outermost part, 4s part. So this 4 is 0. This is the outermost configuration of Fe di positive. This is 3d6 configuration. Let's make this 3d6 configuration. Let's make this 3d6 configuration. 1, 2, 3, 4, 5, and 6, right? If I'll ask you, how many electrons are unpaired? You'll say 4 electrons are unpaired, right? So n value is 4. Put the value of n in this equation, get the value of spin magnetic moment, right? Yes. Put the value of n in this equation, get the value of spin magnetic moment. As simple as that. Yeah. Correct. Similarly, if I have something as Mn di positive, I've got something as Mn di positive. I need to calculate its spin magnetic moment. First of all, I'll be writing the outermost configuration of manganese. It is 3d5 4s2. But this is Mn di positive. That means 2 electrons have been taken out. Take 2 electrons out from here. This is 4s0 now, right? Now this is 3d5. This is 3d5. 1, 2, 3, 4, 5, right? This is 3d5 like this, okay? If I'll ask you, how many unpaired electrons do we have right now? We have got 5 unpaired electrons. Put the value of n as 5 in this equation, get the value of spin magnetic moment. So is it going to be paramagnetic or diamagnetic? There are unpaired electrons, right? Paramagnetic. Para or dia? It's absolutely going to be paramagnetic, right? As simple as that. Okay? In short, wherever mu value is 0, wherever spin magnetic moment is 0, that's diamagnetic. Wherever mu is non-zero, that's going to be paramagnetic, right? I'm sure it's clear to everyone. Yeah? Can you solve these sort of questions? Can you solve these sort of questions? And these sort of questions are frequently touched in your examination nowadays, okay? Yeah? All right, these are few examples. This is going to be your homework. You'll write its answer in the comment section, right? What is the value of mu for Cr di positive? This I've already shown. This is something which I'll show you now. This is cobalt plus 2. Iron cobalt. Cobalt configuration is 3d8 4s2. But this is cobalt plus 2. That means take these 2 electrons out from cobalt. This is 4s0. Now 3d8 configuration. How do I write this 3d8 configuration? 1, 2, 3, 4, 5, 6, 7, 8. Correct? This is 3d8 configuration. How many electrons are unpaired? 2. So n value is 2. If n value is 2, get the spin magnetic moment under root of n into n plus 2. So 2 multiplied by 2 plus 2. 2 plus 2 is 4. 4 2s are 8. Under root of 8 means 2.89 Bohr magnetrons. This is basically the spin magnetic moment. If I'll ask you, is it going to be para or dia? Is mu coming out to be 0 or non-zero? Mu is non-zero. That's it. That means it is paramagnetic in nature. Yeah? Clear to everyone? Let me know fast in the chat box if it's clear. Let me know fast. Absolutely, it's going to be para. Yeah? Okay. Which of the following has the maximum number of unpaired electrons? Can you solve this one? Right? I'm giving you these questions as the homework because I told you the concept, right? I'm not going to solve this question. This is something which you'll let me know in the comment section, okay? Right? Yes? Can you let me know the answer of this question? The correct ground state electronic configuration of chromium atom is? The correct ground state configuration of chromium is? Yes, Giri, I'll be doing that. Wait for it. This is something which I've told you a few minutes back. Let me know its answer fast. Correct outermost configuration of chromium. Is it 3d4 4s2? No, it's 3d5 4s1. 3d5 4s1. I hope you know it. Right? Few minutes back only I told you. Option A is the one which is correct answer of this one. Yeah? Okay. The orbital diagram in which a Bohr's principle is violated. What do you think about this one? That orbital diagram in which a Bohr's principle is violated. As per a Bohr's principle, electrons are to be filled in the orbitals on the basis of their increasing energies. Right? Okay. If you look at this, see, this orbital is completely filled, then we are moving to some other orbitals. If you look at this, is this orbital filled? That's not completely filled, right? So over here, a Bohr's rule is violated. You were supposed to fill this completely, then move to the other orbitals of higher energies, right? Yes, so option B is the one. Yeah? Okay. Any p orbital can accommodate up to? Let me know fast. Any p orbital can accommodate up to? Which option? Guys, see the question carefully. Again, you are making the same mistake. He is saying p orbital. He is not saying p subshell. Right? If it was p subshell, then the answer would have been 6. But this is p orbital. He is asking about one of the orbitals in the p subshell. And we know every orbital accommodates maximum of 2 electrons, that too with opposite spin. So 2 electrons with opposite spin, right? Option D is the one. Again, you are making a mistake. Yeah? Okay, one more. This question was asked in your NEET 2019. This question was asked in your NEET 2019. I'm sure you can solve this one as well, right? You are basically going to arrange these orbitals on the basis of their decreasing energies, right? Which rule you are going to use? You are going to use which rule? Bohr-Bury's rule, right? N plus L rule. For 4D, what's the value of N? N value is 4. L value for D is 2. So 4 plus 2 is 6, right? So N plus L value for 4D is 6. 5P, 5 plus 1, this again 6. 5F, 5 plus 3 is 8, right? 6P, 6 plus 1, that is 7. Okay, these are N plus L values. Now, which is the least N plus L value? This 6 is the least N plus L value, right? But two orbitals have got same N plus L. Now, decide on the base of N. Over here, N value is minimum. So, 4D will have the least energy. So, the answer is either going to be this one or this one. 4D is going to have least energy. Then your 5P, right? Among your 5F and 6P, 5F is going to have more energy than that of 6P. So, option A is the one which is correct among all, right? I'm sure you can clearly solve these sort of questions on the basis of N plus L rule, which we have discussed a few minutes back. Yeah? Okay, this is something which I'm giving you again as the homework. You're going to let me know its answer in the comment section afterwards, right? Okay. One more simple question. Can you let me know its answer? The total number of atomic orbitals in the fourth energy level of the atom. Fourth energy level means fourth shell. Can you let me know its answer fast? The total number of atomic orbitals in the fourth energy level of an atom is? The total number of atomic orbitals, people, in the fourth energy level. Total number of atomic orbitals, few minutes back I told you. Total number of atomic orbitals for a particular shell is always given by the formula n square, right? Which shell we are talking about? We are talking about the fourth shell. So 4 ka square is 16, right? So B is the answer. B is the answer. N square, this is something which I gave you, right? This formula I gave you a few minutes back. I don't know why you're still making it wrong. Okay, the orbitals are called degenerate. The orbitals are called degenerate. They have same wave functions. They have same wave functions but different energies. They have different wave functions but same energies. They have same energies. Well, this is something which you won't be able to solve now because you have no idea what are wave functions. That's something which I'll be letting you know in the next session when I'll be exactly teaching you the quantum mechanical model. Anyways, if you still want to know, the answer is going to be they have different wave functions but same energies. Option C is the one which is correct among all. Prashant, 2n square is the number of electrons, total number of electrons, right? Maximum number of electrons for a particular shell. He was asking about the maximum number of orbitals, right? He was, I guess, asking about the maximum number of orbitals. Orbitals. He's not asking about the electrons. Yeah? Okay. An ion has 18 electrons in the outermost shell, it is. An ion has 18 electrons in the outermost shell, it is. What do you think? Which ion has 18 electrons in its outermost shell? Which ion has 18 electrons in its outermost shell? What do you think? If you look at the electronic configuration of Cu positive, if you look at the outermost, electronic configuration of Cu positive, it has got total 28 electrons. Now distribute these 28 electrons. Now in its outermost shell is its third shell. In the third shell, how many electrons do we have? 10, 6 and 2. That means 18 electrons. So in Cu positive, we have got total 18 electrons, right? Okay. So this was all for today. I'm sure you have enjoyed this session, right? And people, the ones who have not joined into the actual Vedantu classroom yet, please do join it in as soon as possible. Let me tell you, the next batch is starting on Monday, right? I want you guys to join in. I want you guys to join in as soon as possible. Okay? Well, you have got everything in these programs right here. If you look at the first program which we have, for you, okay, let me explain this a bit. If you look at the first program, which is what I call as light program, right? It's valid for 2 years. It's a complete package for 2 years. Let me tell you that. Okay, it's a complete package for 2 years. No need to pay this much of amount in one go. You can pay this amount in the form of EMI as well. Vedantu has kept an option for this, right? At the same time, if you are new to Vedantu, you have no idea how the actual Vedantu platform looks like, right? What you'll be doing is, you can take this subscription for a month, this much of amount, this 2,700 you'll be paying, right? You'll be taking the subscription for a month, see if you are getting benefited, right? And I'm sure you'll be definitely getting benefited, right? Okay, so do take it for a month at least, check it out. You will be definitely getting benefited, and then after that you can go for the 2-year classroom program, right? And what all benefits we have? We have got live interactive classes, we have got test series and analysis. The best part is notes and the study material. That is the best part which you get from here. You get India's best study material in Vedantu, trust me on that. That's what we call as Tattva material, right? You have got one more program which is Classic. What all features we have got extra in Classic? Whatever features where they're in light, apart from that, you get doubt solving on mobile app, right? Even this is a course fee for complete 2 years. You can pay this much amount in installments, right? If you are new to Vedantu, you can just take it for a month, see it first, right? This is something which you have to pay for 1 month, yeah? And at the same time, this is the last one, that is the Plus Pro subscription. This is again valid for 2 years. Why its cost is a bit higher? Because you get personalized mentor in all the 3 subjects. You get personalized mentor in all the 3 subjects, right? Okay, and you can take it for a month as well, see how it helps you out, okay? And I'm sure it is definitely going to be helpful for you, okay? Take one of the subscription, and how to take the subscription basically. There's a link in the description box of the video. You need to click on that link. You need to use the coupon code as WSPRO. If you use this coupon code of WSPRO, you'll be getting some additional 20-30% off as well, right? So do click on the link which is there in the description box of the video. Get enrolled to the actual long-term batch. And there is one more link in the description, that's for the Telegram. Do click on the link, get added to the Telegram group and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Before ending the session, let me show you exactly how to join into the long-term batch, okay? Let me exactly show you how to join into the long-term batch. See guys, this is the video which you guys are currently watching, right? Structure of atom, class 11th, lecture number 10, electronic configuration, right? This one, okay? Now, you need to just drag it a little down. You need to drag it a little down, right? Okay? After dragging it a little down, you'll be getting a lot of links, okay? These are the some basic concepts of chemistry I have taught in detail. This is the playlist of that. States of matter playlist, right? Okay? Download Vedantu free learning app, right? Structure of atom playlist for NEET 2023, you can watch it out, okay? Right? And people, at the same time, if you go down, there are a lot of other links as well. Just give me a second. Where has that link gone? Okay, subscribe to Vedantu Pro now. Okay, you need to click on this link. After clicking on this link, right, you need to choose your plan. For example, I'm selecting the light plan. Okay, yes, try for a month. I'm trying for a month. Okay, I'm going to give my phone number, my email ID, in which I'll be getting the OTP, right, and I'll be continuing. Yes, and during the enrollment, what you guys are going to do, you guys are going to use the coupon code which I gave you, right? What is that coupon code? That is, I guess, WSPRO. Is that? Yeah, right? So with this, I'll take a leave. I'm sure you would have enjoyed the session, right? I'm sure you would have enjoyed the session. Perfect. So let's meet up, people. Let's meet up soon. You'll be getting the schedule tomorrow or day after tomorrow. You'll get to know when I'll be taking the next session for NEET 2023 students, right? It was nice meeting you. Yeah. Let's catch up soon. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye. Yes, Ravni, you can take it for a year as well, right? Just enroll into it, then talk to operational team. They'll be helping you out, right? You can take it for a month, first of all. Take it for a month at least.